In the previous part, we introduced the principle of virtual work, and for both a continuum and for beams. And just to recap what the principle states, it states the following. If I have a continuum, and this continuum is made is in equilibrium, it has an internal or it has a body forces vector applied to it, and on the surface I have a traction vector, or traction vector is Tn, and this continuum has a continuous stress distribution inside. At every point I know what the equilibrium stress is, the stress that satisfies the equilibrium equation. So, and if this object is in equilibrium, and from that equilibrium, if I take that object and I apply a displacement field u star, so every point will move with a displacement u star, and u star is arbitrary, it could be any displacement field, and the associated strain is equal to half the gradient of u plus the gradient of u star plus the gradient of u star transpose. Then the principle of virtual work states the following. The external virtual work, which is equal to the forces multiplied by the corresponding displacements. This is the first force is rho b vector dot u star vector integrated over the volume. Don't forget what the limits of the integration are, plus the traction vector on the surface integrated over the dot product between the traction vector and the displacement vector integrated only on the surface, because these traction vectors are applied on the surface. This is equal to the internal virtual work. The internal virtual work is the work done by the stresses. The internal stresses are sigma ij, and the virtual strains are epsilon star ij, and this is the sum from ij equal 1 to 3. So sigma on 1 epsilon star over 1, sigma to 2 epsilon star to 2, and so on, and this is integrated over the volume. And we showed an illustrative example. So this is the principle of virtual work applied to a continuum. Now when I apply this to a beam, so application of the principle of virtual work. So application of the principle of virtual work for beams. If I have a beam where the beam is in equilibrium, it has an internal bending moment diagram M, it has external load Q, and it has reactions or end reactions V2, M2, V1. Sorry, the positive displacement, the positive convention is V1, M1, and V2 acting downwards on the other end, and M2. Now from this equilibrium, if this beam is in equilibrium, from this equilibrium I apply a displacement, I call it y star, any virtual displacement, such that I have theta 1 star at this end, theta 2 star at this end, y1 star at this end, y2 star at this end, and y star at every point. The principle of virtual work states the following. The external virtual work, which is equal to the distributed load Q, external, multiplied by the displacement y star integrated over the length of the beam, plus the reactions. I have V1 y1 star minus V2 y2 star plus M2 theta 2 star plus minus. And the positive and negative is just according to if the load is in the direction of the virtual displacement or opposite. So minus m1 theta 1 star. So this is the external virtual work. The internal virtual work is equal to the stress multiplied by the strain. The measure of the stress I use is the moment, and the measure of the strain I use is the second derivative of y star, the virtual strain, integrated over the length. And we showed an illustrative example that showed that the internal virtual work is equal to the external virtual work. Now we're going to apply this principle to beams, and we're going to apply it in the case when the internal virtual work is equal to 0. So what happens if I choose y star such that the second derivative of y star is equal to 0? Well, then you end up with the equation that states that the external virtual work will be equal to 0. And I'm going to use this fact, use this to find reactions. Now, how is that possible? I'll show you this using an example. If I have the simple beam supporting a load P at a distance A. So I'm going to utilize the principle of virtual work to find the reactions. Now let's first find the reactions using the sum of forces, using just equilibrium. From equilibrium, sum of the forces in the horizontal direction is 0, and so R3 is equal to 0. Sum of moments around point 1 equals 0, where this is point 1. And so if I have negative P multiplied by A plus R2 multiplied by L equals 0, which leads me to R2 equal to P A over L. And sum of forces in the vertical direction equal to 0, you'll find that R2 plus R1 equal to P, which will lead to the fact that R1 is equal to PB over L, which is equal to P L minus A over L. So this reaction is equal to this force multiplied by B over L, and this reaction is equal to P multiplied by this distance A divided by L. Okay, now I'm going to utilize the virtual work principle to find the reactions. Now how am I going to do this? First, I'm going to apply a displacement, y star, such that y star is a rigid body motion. I'm going to just move the beam horizontally by a distance x1, and then I'm going to rotate it with an angle theta. So y star in this case, this virtual displacement at any point, the vertical displacement is equal to y star at this point. So let's just show you. This is y star, and this is an angle called theta star. And this distance is equal to this distance, which is originally the length of the beam, which is originally x1. And so this distance is sine x1 sine theta. So y star is equal to y1 star plus x1 sine theta. So this is the virtual displacement, the virtual vertical displacement applied to the beam. Okay, so using principle of virtual work. So let's see. The principle of virtual work states that the external virtual work is equal to the internal virtual work. Now the second derivative of y star with respect to x1 squared is 0. Therefore, internal virtual work is 0. Therefore, external virtual work is 0. Okay, let's write the external virtual work. The external virtual work is equal to the first reaction, R1, multiplied by the displacement at this point, which is y star 1, plus, I have a 0 moment here, 0, multiplied by theta 1 star. So this goes, plus the reaction R2, multiplied by the displacement y3 star, which is the displacement at this point, plus, actually minus, the force P, multiplied by the corresponding displacement. I'm going to call it y2 star. What other forces do I have? An end moment is 0, so 0 multiplied by theta 2 star. I have another force, which is R3, multiplied by the horizontal displacement of the beam, which is x1 star. Now I have an equation for y star, so I can find y star 3 and y star 2. Because y star 2, let's just draw the beam again to find y star 2 and y star 3. This is y star 1. Y star 2 and y star 3. Y star 2 is equal to y star 1 plus a sine theta star. And y star 3 is equal to y star 1 plus L sine theta star. Okay, so I'm going to apply all this into the external virtual work equation. The external virtual work equation will then look like this. R1 multiplied by y1 star plus R2 multiplied by y1 star plus L sine theta star minus P multiplied by y2 star, which is y star 1 plus A sine theta star plus R3 x1 star. And we know that this is equal to 0. Now I'm going to group this according to the starred quantities. I want to find what's the multiplier of y star 1. You're going to find R1 plus R2 minus P. What's the multiplier of sine theta star? R2L minus PA. What's the multiplier of x1 star? It's R3. However, y1 star, theta star, and x1 star are arbitrary, which means I can choose any values for these. So if I choose, by choosing y star 1 equal 1 and x1 star equals 0 and sine theta star equals 0, you obtain the first equilibrium equation, r1 plus r2 minus p equals 0, which is basically the sum of the forces in the vertical direction is 0. And by choosing y1 star is 0 and sine theta star equal 1 and x1 star equals 0, you get the second equation, which is r2l minus pa equals 0, which is basically the sum of moments around point 1 equals 0. And finally, by choosing x1 star equal 1 and everything else is 0, you get that the horizontal reaction is 0. And so the reactions are obtained using the principle of virtual work, because these are the same equations of equilibrium. So you can see that this these equations, or the principle of virtual work, when I use it, I obtain the equilibrium equations again, and I'm able to find the reactions. Okay, so let's go through another example. A cantilever beam. So I have a beam. We need to find the reactions R1, R2, and M3 using the equilibrium equations and using the principle of virtual work. So using the equilibrium equations, the reactions are simple. Our sum of forces in the vertical direction is 0. So you get R1 is equal to Q multiplied by L. Sum of the forces in the horizontal direction is 0. R2 is equal to 0. Sum of moments around point A equals 0, where this is point A. So you get M3 minus, or is equal to Q L squared over 2. So let's see how we can use the principle of virtual work to find these reactions. So again, we're going to apply a displacement such that the displacement is equal to the second derivative of that displacement is 0. We're going to apply a displacement such that D, choose y star, choose an arbitrary y star, such that the second derivative is equal to 0. Okay, so a general y star would be equal to y1 star, which is the displacement at the very first point, plus x1 sine theta star. And a horizontal displacement x1 star, just to be able to find the reaction R2. So using the principle of virtual work, the external virtual work is equal to 0, because the internal virtual work is 0, because the second derivative of y star with respect to x1 will be 0. The external virtual work is equal to the volume. First, I have a distributed load Q acting downward, so I'm going to put negative Q. And I'm going to put the displacement y star, which is given by the equation integrated over the length. So this is the external virtual work by the distributed load, plus vertical reaction R1 multiplied by y star 1. I don't have any reactions on the free ends. I have R2. I have a moment acting this way. Rotations are always assumed this way. Theta star, so M3 multiplied by theta star. So this is equal to 0L negative Q Y1 star X1 sine theta star so this is equal to negative QL Y1 star minus Q sine theta L squared over 2 plus R1 Y1 star. Oh, I forgot the horizontal reaction. So R2 X1 star plus R2 X1 star and this is equal to 0. So again, I'm going to pick the multipliers of all the starred quantities. So the external virtual work, which is equal to 0, will be equal to, I'm going to pick Y1 star, and the whatever is multiplied by Y1 star is negative QL plus R1. I'm going to pick X1 star, R2. And I'm also going to pick sine theta star or theta star. But since I see both sine theta star and theta star, I'm going to choose theta star very small, such that sine theta star is equal to theta star. Since sine theta star is equal to theta star, so theta star is small, or chosen small, such that theta star is equal to sine theta star. Sine theta, so this will be give me M3 minus Q L squared over 2. And similar to the previous section, these quantities are arbitrary. I could choose anything I want. If I choose this 1 and this is 0 and this is 0, you get R2 equals 0. If you choose by choosing y star 1 equal 1 and x1 star equals 0 and theta star equals 0, you get the equilibrium equation that says R1 is equal to QL, which is the same equation that we used to find the reaction using the equilibrium equation. And similarly, M3 is equal to QL squared over 2. And as you can see, the principle of virtual work, in essence, is a representative or is the same as the equilibrium equations, because of the arbitrary nature of the chosen virtual displacement, I can retrieve the equilibrium equations. Now, the same principle, you use it in other classes. For example, in 372, the principle of virtual work is used to find displacements at specific points for linear elastic small deformation beams when especially for statically determinate beams. So how is this done? It's done as follows. Given a beam with loading and reactions, and I'm interested in finding the displacement, for example, at this specific point. I'm going to call this y1, and I would like to know what this y1 is. So to utilize the principle of virtual work, I'm going to do the following. I'm going to create another beam and apply a load here. I'm going to call it 1. And after applying this load, I'm going to call this displacement of the structure, and we're going to call this y. And I'm going to call the displacement of the structure y star. And then I'm going to say the internal virtual work is equal to the external virtual work. The internal virtual work is chosen is equal to the moment produced by the first configuration, m1, multiplied by the second derivative of y star with respect to dx1 squared, integrated over dx1. And the external virtual work is equal to the forces, which is 1, multiplied by y1 star, plus the reactions multiplied by the corresponding y star at supports, but at the supports y star for this application is 0, so this goes to 0. And so you end up with the internal virtual work is equal to the external virtual work, so the internal virtual work will be equal to the integral of m1, the second derivative of y star, which is basically what we call m0 over ei dx1 integrated from 0 to L equal to 1 multiplied by y1 star, which I'm going to call delta star. And delta star is the unknown. I know the bending moment under one load, unit load. I know the bending moment under the current loading on the structure. And when I do this integration, I find the displacement. So let's do it. Let's apply an example. Find the vertical displacement at the cantilever end due to the loads shown in the figure. So in order to apply the principle of virtual work, as you do it in 372, the external virtual work is equal to 1 multiplied by delta star, where this is delta star. This is equal to the integration of the bending moment m0, m1, multiplied by the bending moment m0, divided by ei, integrated over the length, so I need to find m1 and m0. When I put 1 here, m1 will be equal to negative L plus x1, because the bending the moment is equal to this is x1, this is x1 minus L. Actually, this is equal to, so if this is the beam, and the applied load at the end, I'd like to find the moment here. The moment here, this distance is equal to x1, L minus x1, and this is x1, and so the bending moment is equal to negative L plus x1, because we assume that this is the positive moment, but it's actually acting downwards, so negative L plus x1. M2, on the other hand, you need to solve the beam with the applied load, so I have Q M naught is equal to negative Q L squared over 2 plus Q L x1 minus Q x1 squared over 2 . So this is M naught and M1. Let's just draw M naught. It looks like this. So this is M naught. And so applying the virtual work principle, 1 multiplied by delta naught is equal to 0. The integration from 0 to L, M1 is equal to negative L plus x1. M naught is equal to negative QL squared over 2 plus QL x1 minus Q x1 squared over 2, integrated over the x1. And from here you find that delta star is equal to QL power 4 divided by 8 EI. And so you will not find this application in your exams because it's covered in different courses. I'm just showing you that this application, how it relates to the virtual work principle, or how it's derived from the principle of virtual work that we talked about in this in 398. The final example, which is the most important application for the virtual work, is finding approximate solutions, which is what we will talk about in the next part of these lectures.